Hello, everyone. Thanks for watching the video. It's kind of an interesting experience to give the talk virtually and also record at home. This is my first time doing it. I am Tengyu from Stanford University. I'm an assistant professor here, doing mostly machine learning theory, some of the empirical and theoretical aspects of deep learning, which I'm going to talk about today, and also some of the deep reinforcement learning algorithms. I guess you can find my papers and work online on my website. And today my topic is about deep learning for small, imbalanced, and heteroskedastic datasets. Speaking of deep learning, I guess let me start with talking about the kind of magic formula that we have witnessed in the last 5 years about deep learning. The kind of formula is that you want to grow your datasets and your models simultaneously as much as possible, and also probably want to buy a lot of machines to do the compute. So I guess clearly this is not scalable for all of the applications, right? So here I'm having some of the vision and NLP applications and datasets, ImageNet, Wikipedia. So ImageNet has a many examples. This is considered to be somewhat large for academia scale, but actually it's probably very small for industry scale. In many of the companies, actually, there could be hundreds of millions of labeled examples internally for them to train their vision models. And there could be even more unlabeled examples in natural language processing. So for many other applications, actually, we don't have so many examples, not even unlabeled examples. And what we can do there? So I guess the main point of this talk is that what we can do if we only have small data. Do we have to just give up deep learning and go back to linear models, which then sounds to be super impressive in these days? Or I can still leverage the power of deep learning in some way to some extent. I guess the answer is yes, we can indeed still use deep learning for small data with some additional techniques. Before talking about techniques or solutions that we have for small data with deep learning, maybe let me talk about what's the issue with small data. So the issue is obviously overfitting to the training data. This is a classical phenomenon. When you don't have enough data, then you are going to overfit to your training data in the sense that you are going to memorize all your training examples, and the model you learn will not generalize to unseen test examples. Here, I'm only having a linear model actually, and so that I can run everything efficiently and have this plot for ablation studies. So on the x-axis, I have the number of data points. On the y-axis, I have the number of the test errors. And you can see that with 50 examples in this case, you get pretty good test errors. But if you only have 20 examples, then you're going to have worse test errors. And actually, one of the other interesting phenomena here is that you have this non-monotonicity of test errors in number of data points, which is often referred to as the double descent phenomenon these days, and attract a lot of attention from machine learning researchers. However, here, this is not the main point. The main point is just that, if you don't have enough examples, then you're going to have worse test error. And one of the classical way to fix this is to use the so-called regularization technique, which effectively restrict the model complexity by adding some additional term in a loss function. And this can improve the test error because you are restricting the search space. So you are less likely to memorize all the training examples. So typically, the form is like this. You add something like lambda, which is the regularization strength, times a so-called regularizer. Here, I'm choosing the regularizer to be the L2 norm square, which is basically the sum of squares of your parameter theta. And you can start with lambda 0, which means the original training loss, which is shown here in the purple color. And you can add more and more lambda. You can use bigger and bigger lambda to get better and stronger regularization. And you can see here, if I add a little bit lambda, then I'm going to have a little bit stronger regularization, and my test error improves, especially for 30 number of examples, the test error improves dramatically. And if you have more and more regularizations, then your test error will continue to improve, and so on and so forth. And you can see, actually, the interesting thing here is that it requires more regularization when you have smaller number of data points. So if you look at 18 examples, then more regularizations always helps. However, if you have 42 examples, then it's not clear whether more regularizations helps. Actually, sometimes more regularization can hurt because you already have so many examples and you don't really need the regularization to restrict your search space. So the bottom line is that smaller data means you want to have stronger regularization. So the next question is, what's the right form of regularization I have to use? Right, before in the last page, I'm using the L2 regularization, which is just the sum of squares of the parameters. However, for deep models, it's unclear this is the best one. And actually, it's not the best one because we know that L2 regularization is pretty weak for deep models for various reasons. And for deep models, you want to use some other regularization, for example, job halt. This is a very popular approach, which is widely used for NLP, especially, and also for vision models. And also data augmentation, which is often useful for vision problems, such as mix-up, cutout, random augmentation. And also I'd like to mention one of the regularization technique my team has studied and proposed. This is called NeurIPS regularization. So basically, the idea is that you want to encourage the model to be continuous and smooth so that it can extrapolate to other test examples more smoothly. So in some sense, this is a non-parametric techniques similar to non-parametric statistics, but you really have to do it in the right way for deep neural network models. And if you do it in the right way, then measure the smoothness in the right way, then you can get pretty consistent improvement of test error. So here, the smaller the better. So we test on CFAR 10 and CFAR 100, two very common vision baseline, and we can see consistent improvement in many different settings, including noisy example settings. We have tested this on other baselines as well. And this data augmentation so this regularization technique also can be used together. So data augmentation can be used with NeurIPS regularization as well to get even better results. So the next question is how to regularize. How much do we regularize? Right. So we have talked about how to regularize, with what kind of form. And the next question is, what regularization strengths you want to put in. Recall that, for linear model, for most of the regularizations, the form is that you have training loss plus lambda times the regularizer, and lambda is the regularization strength. So the classical learning theory for linear model tells us that lambda should be chosen to be sigma squared over n. Here, sigma is the noise level in the data set, meaning how much noise in your data set, in the labels of your data set, how uncertain your label is. And n is the number of data points. You can see that this is consistent with our observation before. The smaller the number of data points you have, the larger the regularization strength should be. And also your regularization strength should be bigger if you have more and more noisy data. The story is a bit less unclear for deep models because it's very hard to reason about deep neural networks. It's non-linear and complex. However, the general trend seems to be very similar. Noisy and small data implies that you want to use stronger regularization. So again, it sounds like the solution is pretty simple. We just have to use this intuition to tune our regularizer strength on the validation set and until you find the best choice of regularization strength. So, however, in reality, the story is not that clear. The main issue is basically that in reality, you have some heterogeneity in the data, so that sometimes actually you cannot tell the difference between small data and big data, just because your data is actually a mixture of small data and big data in some sense. So the realistic real-world data sets often are imbalanced, meaning it's actually a mixture of small data and big data for various different classes and groups. For example, suppose you have some kind of neuroimaging data set, then maybe the positive example is much more often than the negative examples. So it's much less frequent than the negative examples. You have way more negative examples than positive examples. So for positive examples, you can think of this as small data, but for negative examples, you think of as big data. And also in some other cases, you also have this so-called heteroskedasticity in your data set, which means that you have a varying level of noise in your data set due to annotation error or ambiguity. Some groups of examples may have very unreliable or very noisy labels, just because those are very hard examples to label, and the labelers don't really know what are the right choice of labels for those examples. And for some other examples, maybe the label are very reliable. So just to give another real world situation. So here, this is an example of object recognition of street views. You have these different pedestrians, buildings, roads, and different kind of objects in the street view that you want to recognize. And if you look at the histogram, or if you do some basic statistics of how many pixels of each object show up in this data set, you're going to see that it's very imbalanced. So basically, every picture in this data set has a road in it, and the road is pretty wide, pretty long. So there are a lot of pixels in the road class. So in some sense, you really have big data for road. And also note that the y-axis here is in logarithmic scale. So the road is very much more often than some of the other classes in this plot. On the other extreme, so bicycle is kind of like small data. So the reason is that not all images has a bicycle in it, and also bicycle is pretty small. So bicycle tends to have relatively small number of pixels. So in some sense, you don't have enough data for learning bicycle. And we have this mixture of big data and small data. Choosing the right regularization strength becomes problematic. If you use too big of a regularization, then you are in the big data, you are doing pretty well for the small data, but you are hurting the big data. And if you use too small for regularization, then you are doing pretty well for the big data, but you don't, you overfit to the small data. So how do we choose the right regularization strengths for imbalanced and heteroskedastic data sets? So here is an example, right? So just to flesh this issue out a little bit more. So on the left-hand side, I have these kind of data points that are frequent and very clean. So here, the blue curve is the ground truth, and the blue points are the data points. On the left-hand side, these examples doesn't have any noise in it, and also there are a lot of examples. So these are frequent and clean examples. On the right-hand side, you have infrequent, rare, noisy examples. So if you choose the regularization strengths, then you can choose either weak regularization or strong regularization. Here, for example, we have some parameters for the regularization strengths, and you can see that if you use the too weak of a regularization, then what happens is that you do pretty well on the left-hand side for the frequent and clean examples, but you don't do very well on the right-hand side. You do trim pretty well, you fit to those examples, but you don't generalize because you just overfit to the noise on the right-hand side. However, if you use a strong regularization, you do much better on the right-hand side because you can extrapolate and you restrict your hypothesis class so that on the right-hand side, you fit some more sensible curve, even though still the error is not great. But on the left-hand side, this is terrible because you are underfitting. You really want the model to be very Lipschitz, very smooth, and then you underfit the W shape on the left-hand side. So the idea that we have is that we say, probably you want to get the best of the two worlds by doing something more clever. So what you do is that you want to say, why not using different regularization strengths for a different part of the space of the model? So basically what we do is that we use a different regularization strength called lambda I for each example in this plot. And the principle is that if xi has a noisy label, or if xi is rare, so these are the cases on the right-hand side, then you use bigger regularization. And if xi is clean example, or if xi is a pretty frequent example, then you use a smaller regularization as on the left-hand side. So then you can get the best of the two worlds. So how do we exactly choose this regularization strength lambda I? So we did some theory to try to figure out what's the right formula for lambda I. So here we are having a 1D case, and the formula for lambda I is this. So here on the top, this I sub I is measuring the uncertainty of the label of xi. And on the bottom here, so the Q sub I is measuring the density or the frequency of the example of xi. So basically this is saying that the more uncertain the label of xi is, then you want to use stronger regularization, and also the more frequent the example xi is, you want to use less regularization. And empirically, what you do is that you use some empirical methods to estimate I sub I and Q sub I, and then you plug in them into this formula, and then you optimize the adaptively regularized training loss. What you do here is that you have training loss plus a term, which is the sum of lambda I times a regularizer. So here the important thing is that the regularizer needs to be dependent on the data points so that you don't kind of merge this sum into a single term. So every regularizer depends on theta and xi. And actually what we do here is that the regularizer is the smoothness of the model on the data point xi. And you have different lambda I in front of them according to the formula. And if you do this, then you're gonna have better models for both the left-hand side and right-hand side. On the left-hand side, you don't regularize much, then you fit to the data, great. And on the right-hand side, you regularize a lot so that you don't overfit to the data, and you get also some sensible right curve here, as you can see. So we have tested this idea and this algorithm on many other data sets as well. So one thing you can do is you can test on CFAR10 with a level with some synthetic level of heteroskedasticity. So we just create, different subgroups of different level of labeling noise artificially. And then you can see that if you run these experiments, you will see that, we get consistently better test accuracy compared to many other data sets. And here, particularly, you can see that the improvement mostly comes from those noisy classes than clean classes, which means that we are allowed to use stronger regularization for particularly the noisy classes, and you improve the regularization, the generalization for those classes. And you can also combine heteroskedasticity with imbalance, and then you see that you also get even bigger improvement compared to prior work. And indeed, the improvement on the noisy and rare classes compared to, more on the noisy and rare classes compared to the clean classes. We also test this on some real world data set without artificially created imbalance and heteroskedasticity. So here, this is a data set called Web Vision, which consists of kind of a few million examples, and the labels are crawled from the web. So the labels are pretty unreliable. There are a lot of noises in the label. And also there's an imbalance because naturally the images on the web are imbalanced. So, and so this is a real world data set. We didn't do any artificial post-processing of the data set. And we can see we get pretty good improvement compared to previous state-of-art methods. We also have done more experiments on other vision and NLP data sets. So I guess, this is pretty much all the experiments I want to show. And just as a summary, so today I talk about, the regularization techniques for small, imbalanced, and heteroskedastic data sets. You want to regularize different examples differently according to their noise level and the frequency of the examples. And looking ahead, there are several other techniques that I'm very interested in. Some of them are we are working on. So let me just briefly mention some of these, other techniques I'm interested in that can help solving small data sets. So one question is, how do we use a related large data set to help us learn a small data set? The buzzword here is domain adaptation and transfer learning. We want to transfer the knowledge from a large data set, which is not necessarily on the same task, to the small target data set that you are interested in. And the second idea that I'm very interested in and I'm working on is about how to collect a small amount of informative data actively. So many of the data sets are not designed in the best way, right? Because there are some repetition in the data set. Some classes are very popular and some other classes are very rare. So you have this imbalanceness because of the data set design. And if we can design the data set much better, then possibly we can have a smaller number of examples, but can still learn from the small number of examples to extrapolate to unseen other situations. So the buzzword here is active learning and datasets design. And the general idea is to somehow choose those prototypical examples instead of repetitive examples. So these are some of the ongoing work we have done, and also of course we are interested in how to do the regularization much better for other kind of data sets. Every data set has their own properties. The imbalanced and heteroskedasticity are just two properties, and maybe some of the other data sets have other properties. We also want to use regularization techniques to improve those properties, to leverage those properties. Okay, so I guess this is all I wanted to say. Thank you very much for listening, and looking forward to seeing you at the live session. Thanks.